5.2 kilojoules.
5.2 kilojoules, that's not small.
See, now Giuliano studied, you understand.
Professor Dash, well, again, the microphone back there, I had a question about your criteria, current load and flux. How close have you come with the flux, and how do you measure that?
Flux is the ugliest of all, and we're barely in control. We're in control of the current. We're barely in control of the loading. We're not at all in control of the flux. We've made attempts to deliberately oscillate the loading level by fluctuating the temperature, oscillating the current. It's very, very difficult to achieve stable oscillations in the loading, which is what you must have if you have a net flux through the interface, by any means, which doesn't result in a net deloading. What tends to happen is you never gain as much on the up as you lose on the down. So the cycle just takes the cathode down in loading. So we are not able to produce the fluxes that natural effects within the system produce.
Back here, and then there's a question over there.
Do you think the surface to volume ratio is any bearing on achieving success with laying cathodes?
And it stands to reason that it must. We haven't explored that variable very carefully. Most of the experiments that we've done have been with cathodes between 1 and 3 millimeters in diameter, so that the range of specimen geometries that we've studied is quite small. We have worked with the plates and foils, and in some cases been successful, but our vision is to make this experiment as simple as possible. I very much echo the thoughts of Daniel Dotzi in the first paper of his conference. In an area as complicated as this and as controversial as this, you need some simple truths in very simple experiments. So we've stuck to as few variables as possible.
So you don't see any real difference between the 1 millimeter diameter and 3?
There is a difference, and a real difference.
What's the difference?
The difference is swamped by the differences in the variability of the metal supplies. But the first, most successful series of experiments that we performed was with a 1/8 inch wire obtained from Engelhardt, which we machined down to 3 millimeters. And we stuck with 3 millimeters for a very long time. Latterly, we have used 1 millimeter wires because they load more quickly, but we haven't really been quite as successful with 1 millimeter. But the statistics on that are quite poor.
Next question here. Yes.
Mike, sorry. We observed the same behavior as in yourself.
That's a shame.
By increasing the current, sometimes the loading decrease. Do you think that also the bubble formation for a particular configuration can start the electric field configuration in producing this effect?
Well, we are not really able to observe the cathodes at the times that they're doing this, but a conjecture is that the high loadings are obtained only because a surface film of a particular structure has been formed on the surface. To explain such an explosive deloading process, you need a mechanism with positive feedback, and I suppose that at a certain point one part of the cathode becomes incapable of maintaining that high activity, bubbles start to form, and you get a mechanical disruption of the film that was otherwise doing good things for you. So now the film is essentially blown off the entire surface and the cathode deloads. So I think there are mechanical effects due to the bubbles which contribute to our failure. Doesn't explain why we were successful in the past though, and what was the difference. With cathodes that are able to maintain the loading at high current densities, what's the difference in that case?
Thank you. We're going to coffee hour. My co-chair has the last question.
I'm taking advantage of being a chairperson. So, I'd like to ask a question. You showed us the experiment LL5. I think to my category, it is a very nice data, but you are still complaining that the data is still not satisfactory comparing to the data of P15 and P16. But as far as I remember, in your data published in the past, like P12, P13, and C1 and M4, all were producing excess heat under less favorable condition than LL5 as far as I understand. And I would like to have some comment on this point.
I don't know that that's true. You've probably analysed our old data better than I have, actually. But this deloading is abrupt. So the average loading of the cathode went from 0.97 to 0.991, let's say, in a couple of minutes. That meant that the surface went to 0.8 almost instantaneously, because we measure an average loading, and in the dimension of the cathode, the bulk simply can't have deloaded that rapidly. The surface must have loaded. So if we're looking at a surface phenomenon, then it's gone. The surface is sitting there at 0.7. The bulk is sitting there at 0.97, but if you imagine the diffusional field as the deuterium leaves the cathode, the surface must have gone to a very low activity in order to promote this. Now this is a strong transient trend as the rest of the bulk catches up to the damage that has been done to the surface. But our previous experiments, we would say a resistance ratio of 1.7 is interesting.
So we start the session by the report of Professor Box from India on the Icarus 9 calorimeter summary of the design, testing, and operation of this device at the IMA Neuroscience Center.
Thank you very much. A few years ago at Emory, we were faced with a set of experiments in which we
Coming.
very slowly. We were faced with analyzing a group of experiments that were made in our traditional isoparabolic calorimetry, in which towards the end of those experiments, when the input powers were approaching the order of 10 or 11 watts, and the cell was approaching the boiling point, it was very difficult to measure excess heat because of the loss of accuracy and also because the cell contents would begin boiling and boiling out. The energy efficiency of the calorimeter then was very low. It was impossible to contain or carry on studies at these high temperatures, and we thought for a long time that it was important to characterize these reactions which we had observed previously at or near the boiling point in order to investigate the possibilities of the effects of higher temperature on practical use to store excess heat generation. So about that time, Professor Fleischmann, due to those reasons, designed a calorimeter very similar to this schematic, which is shown here. This calorimeter is a double linear, it's a linear heat flow calorimeter. It is composed of a metallic outer casing. The entire calorimeter is submerged in a thermostatic bath, which is held to within 1 or 200ths of a degree centigrade. The principle of operation is quite simple. The lower, it's divided into two sections. The lower section, which we will call the reaction section, is more heavily insulated on the interior. The insulation will be this white area. The glass or quartz cell is held in the center. That is in close contact then, or thermal contact with a jacket, aluminum jacket or a steel jacket or a metallic jacket, separating that inner jacket from the outer casing is then an insulating material. So you can change the thickness or the quality of the material in this insulator gap. You can change the thicknesses of the inner and outer metal layers. You can change, similarly in the upper section, which we'll call the measurement section or the distillation section or condensing section. It's essentially the same construction, except normally you have a thinner layer which gives rise to a higher heat transfer coefficient, and therefore you're able to condense the liquid, the boiling liquid, or the hot liquid, and retain most of the cell contents, which of course will condense back down at the bottom. So we have no evaporative losses of the, at least to the boiling point. Again, that depends on the total power input. The early calorimeter which we built was stable up to about 100 to 150 watts on that order. They've now been somewhat redesigned, made a little bit larger, and with different thermal transfer characteristics, we're able to calibrate these up on the order of 350 to 400 watts. So the principle is quite straightforward for making measurements. It is simply that you are dependent on calibrating the temperature of the contents of the cell at various vertical locations. The theory is that we expect closely straight linear transfer through these through the conductance paths on the bottom half and the top half. You assume that that is linear, and then calibrate the entire calorimeter by putting known amounts of heat in on a known electrochemical system or with electric heaters and by other methods, which we'll talk about in just a few minutes. So we are faced then with putting thermistors in the cell. We are then also placed thermistors in the inner jacket and the outer jacket, so we can measure directly a temperature difference between the outside and the inside of the cell. And we can do the same thing in the upper half of the measurement section of the condensing section at various vertical positions. In the center of the calorimeter, we can put a plug, a condensing plug. This can also be considered as a device for controlling the amount of condensation or the linear heat rise in the calorimeter. As I will show in a few minutes, this has been modified as well. And so then what you're faced with each time is, after it is assembled, to generate a set of calibration curves. It's an absolutely calibrated system. The calibration curves typically will look like this. Professor Oriani, can you read these?
No.
Okay. This is the change in temperature that you measure, the difference in the inner compartment and the outer compartment of the cell as a function of the input power. This is the kind of calibration which you want to end up with. So you will know what your cell input powers are, and at each point, each input power you would then calibrate by measuring the difference in temperature on the inside and outside of the cell. The principle itself being quite straightforward. So we will have a bottom set of thermistors which are located in the reaction section of the cell on the bottom. Typically we run a minimum of 2 thermistors, one located about a fourth of the way up the upper section of the calorimeter. So you have an internal and an external thermistor pair there, so we measure the temperature difference. And then at the very top, which is very high up in the cell, then you will have a third set of measuring thermistors. As you put power into the calorimeter, the temperature for the lower set goes up almost linearly. When you start to get up near, in this particular example, near 50 watts, 50 or 60 watts, the temperature approaches boiling. And of course, no matter how much power you put into the calorimeter at that point, you will always measure a temperature difference by this, according to this horizontal line here, because you cannot raise the temperature of the vapor higher than the boiling point. A similar effect happens at the next thermistor, this middle step thermistor, that is the black curve here. It will not be so sensitive because the liquid is still quite cold and the measuring thermistors are quite far away from the hot liquid below, from the vapor. However, at some point, as the vapor starts rising in the calorimeter, you will start to measure an increase. You will have its maximum sensitivity in this region, and then the sensitivity will start to slow down, of course, as you come to equilibrium at the boiling point. The curve is delayed somewhat, of course, because the rate of rise of the vapor is then dependent on the power input, not on the temperature at the bottom of the power input. The same thing with the third step. The third step, which will also increase, but it being located a very long way away from the reacting liquid or the electrodes in the bottom section, the response is quite much less at that point for that set of thermistors. I'll come back in a slide in a few minutes. This is a close-up photograph of the system as in operation. Typically, we will run 2 calorimeters in a very large water bath with the connecting electronics and the switch boxes, the power supplies, and data acquisition system located above. The room temperature is also maintained very close to the bath water temperature, so that we minimize the fluctuations in the bath temperature as well as minimize any conduction paths in the top of the cell. It doesn't make much difference as long as you calibrate everything under a given set of ambient conditions, both the bath temperature and the room temperature. The main thing is keep it all controlled for each calibration and follow that each set of measurements. Let's look at a wider angle photograph showing the cooling unit. We're able to use 2 cells in a bath now. Previously, we could only use 1 because you have to have a bath cooler, which of course has enough heat removal capacity in order to not let the heating of the calorimeter change the bath temperature, which of course after you exceed the rated capacity, you certainly can't do. These hoses are leads covering the thermistor. Those are, in this particular set of calorimeters, those are the thermistor locations, one in the top of near the top of the boiling cell, and the other 2 located above. The 2 sections being thermally insulated from each other, clamped together with an O-ring. And you see a picture of the window there. We use the window in order to be able to see the level of the electrolyte in the cell. So typically, a typical protocol for making a set of measurements is to apply constant current. We do control power and control voltage experiments as well, but a typical experiment is maintaining a current density of somewhere between 20 and 100 milliamps for an extended period of time. In this particular, this is a very low power experiment as it turns out, but basically the protocol is the same for all experiments. You maintain a constant current, and at some point after you've charged this for a very long period of time, similar to the way some of the other experiments you've seen in some of today's lectures are performed, we then step the current to a higher value and then observe the long-term effects. The potential, of course, is measured during the same experiments. These are data from a much earlier experiment. These fluctuations in the voltage are quite well understood by the decrease in the cell volume with time. The power that is calculated is the product of those 2. This is, as I said, it's a low power experiment. You see very little difference in the bath temperature. This is on the order of, this is the actual top end of the thermistor temperature as the power is changed as a function of the method of the experiment. This experiment running 90-some days, so that's one measurement you get. That's to be compared with the temperature of the outer thermistor located at the same horizontal position, at the same vertical position, and that temperature on the outside, of course, is always very close, within 1 or 2 hundredths of a degree of the bath temperature. Same thing for the middle thermistor temperature, which is somewhat higher because it's closer to the warm solution in the bottom, by the rise in the vapor. And of course, then you have the bottom inner thermistor temperature, which is approaches the cell temperature. It's separated from the reacting liquid by the quartz tube, as well as the quartz cell, as well as the some thickness of aluminum between that glass cell and the inner electrode location in the metal. And the bath temperature is held to 100th of a degree, 1 or 200ths of a degree. These fluctuations are due to variances in the air conditioner, also the air conditioning system, as well as the changes in the feedback system of the this particular cooling unit. These have all been removed now later in experiments by various servicing, which we've done to both the quality of both the thermostat heating units as well as the air conditioning system. One important point that should be made is that the cell then can be modified As you can see, these calibration curves can have various levels of sensitivity. This is very good for low powers. This one is better for medium powers, and this is better for the higher powers. It may be, though, that you're, depending on the final input power, the point at which the cell is boiling, or the operating temperature you want to make the measurements, you want to shift the sensitivity of these curves. In other words, for instance, the top set, if you're working at low power, you may want to shift it back in this direction so you can look more accurately at the top set with respect to the middle set. You have your maximum sensitivity for the middle set in this region, and the maximum now in this region. They're closer together, so you can use comparison of these thermistors in order to get more accurate and confirmatory results between the various sets of thermistors. So the point is, you can change the lay time, or the onset of rise in temperature. You can change the sensitivity. You can even change the various sensitivities, the absolute magnitudes of the sensitivities, by changing various segments of the calorimeter. Specifically, you can change the structure and the materials used in the center condenser. You can insert insulators across the entire barriers, making further separations. This helps in linearity. You can cool these bottom sections with respect to the top sections by putting thermal shorting bars, in other words, rings, metal rings. You can open up the center of the insulating material, the condensing plug here, in order to get hotter vapor to the top thermistors. You can make changes in the insulating material itself. They do not have to be a single insulating material, but you can change the actual quality of the material, the thermal properties of the material itself. You can also change the depth, for instance, the vertical location and the depth of the thermistor ports. These are the inner thermistors and the outer thermistors. You can change those depths and also then change the sensitivity. One problem earlier, well, it's not a problem, but in order to increase the time response of the calorimeter, as the upper section starts to get hot here, it takes some time for the heat to diffuse to the top at a given power, and therefore it takes some time to come to a linear thermal equilibrium. So to increase the time response, you can take into account some of the variables that I just mentioned. Changing those variables, and you can also change the linearity as well as the time response of the device. And that's how you change the sensitivity of those calibration curves. In calibrating, we impose a power on the calorimeter as well as and measure that as a function of time, and we do the same thing. Then we measure the temperature difference at the same time. You will then have many points at that particular power, many temperature points. You can then plot the power against the current, and you will get a curve something like this. This being the points that you saw in the curved portion, the unsteady state points. So the unsteady state points then this is a steady state calorimeter. As I said, we want to get rid of all the time dependency of the unsteady state in order to make a steady state measurement. In doing that, then you can eliminate these points which contribute to the known determinant error. And in doing that, you then arrive at a spread that looks like this for a given temperature and given power. You can then do statistics on those, on that spread. You can determine the confidence limits and the prediction limits for that. You can look for the point of inflection of the confidence limit curves, which gives you a good estimate then of the actual power, the average power, and the straight line fitting through the points gives you a good estimate of the middle set of the temperature. You have to do that for each one of the sets of thermistors. You can then do a histogram analysis, which will give you then the mean and the standard deviation of both the temperature difference and the power input. So you can see that we have standard deviation, for instance, on the power of 0.03 out of 5.06 watts input. So you do that for every point. You then, point by point, build those three calibration curves, and then you run various experiments. In doing experiments, this is a typical result. You measure the top thermistor temperature difference versus that calibration curve. And for blank experiments, or experiments which show no excess heat, you expect to see a curve like this. All these negative points are due to the addition of solvent and the time. So those are non-steady state points. Basically, on these graphs, when you see concentrations of black, because there's so many points, this, for instance, has 32,000 points. Those are more in the steady state. So you get curves like that. You get curves like that for the lower thermistor set, the bottom thermistor set, the top thermistor set. Then for the analysis, quickly. For the analysis then, what you are interested in doing, of course, is then extrapolating those points. You can calculate then, you can look at the power, excess power, then as a function of of time, if you like. And in this experiment, you can see that in this particular experiment, there's very little. These fluctuations are due to the addition and recovery of the input of solvent as a function of time. The average there is 0. I won't have time to show the rest, but they will also do the same for all sets of thermistors. Let's see. Now, I'm reporting on 8 experiments today. As usual, about 89 slides per time. Let's see. Okay, so this is a summary of all the results of the various experiments which we're talking about today. Looking at the middle thermistor, because that thermistor was especially sensitive at the operating input powers, and we find for that particular experiment there's no significant deviation to 0. This is a calculation of the middle thermistor excess power as divided by the input power multiplied by 100. So we have more noise here, of course, because the power input is much less. The same thing for another experiment. No excess power for that experiment. There's another one here, another one here, and we have a set of 3 experiments. The scale here is not good for the slide because it's we purposely included all of the data points, not just taking away the ones that have known determinant errors. But as you can see, this is near a 200% increase of excess power with respect to the input power. The temperature program for that shows the same thing. There's a very large deviation in the possible duration for some 70 days in this experiment. A similar experiment is shown in this slide, where very soon after the racing of the potential, which had been run for this electrode charge for 33 days, again, there was a very large high percentage excess power noted in this experiment. This is when the experiment was terminated. And, well, I better come on to the summary. There's one more in this particular group that shows large excesses of enthalpies as well. This slide is the summary of those experiments. The ones which are in red denote the excess power. The experimental time in days is given here. The maximum powers for minimum of 4.2 hours gives 101 watts in this particular experiment, 17.3 here, 74.5. These two experiments are not yet finished, by the way. The average power is given next to the bottom point, and the percentage excess power is given there, but I have not yet calculated, didn't calculate for that, but I think it's on the order of about 80% as well. Okay, I better come.
Stan, have you by any chance got a slide which shows the temperature excursions in? Have you by any chance got a slide which shows the temperature excursions in the different regions, rather than the summary slide showing the excess power?
I have some calculating sheets. I'll be very happy to show that at any time.
You have not shown transparency.
I don't know if you can see, not as transparency, no, but you can see. If you can see that, no, I cannot see that. But I do have some of those. I can do some.
Is your calibration done with everything inside the calorimeter?
The calorimeter is done with platinum electrodes for electric heaters. We've also gotten away from these large fluctuations by an automatic metering peristaltic metering system, which puts in around 10 milliliters per day for 1 amp. So the fluctuations for the temperature is not very much lower.
Do you find any variation of the calibration depending on the spatial distribution of power generation?
With the spatial distribution
of power generation? Suppose, in other words, the calibrating here is...
You let it come to thermal equilibrium. You let the time constant now is down to around 3 hours, so you may get any effect you like in the first 3 hours, but after that 3-hour period, you see nothing but flat input power, flat temperature.
And it really goes where the heater is with respect to the axis of the calorimeter?
I'm very sure it would be. I'm very sure it would be. So we always keep the electrodes in the heater exactly where the calibration. We've not done a systematic investigation of that. Certainly we have enough blank experiments or experiments which have shown no excess to substantiate that statement.
Please, can you know what is the current density during the excess heat period?
Well, see, the ones I've shown here for 10 millivolts, the charging is always done at about 20 to 100, and we increase the current by a factor of 5, so it would be 5 times 20 or 5 times 100, so it would be up to 500 milliamps per square centimeter.
Are these nominally identical experiments with the same cathode material and everything else the same? And do you have a hypothesis why 5 out of the 8 failed to give excess power?
We have begun on these particular electrodes to re-anneal at a high temperature, vacuum anneal at high temperature. all three of these experiments in red, we have gotten results in our earlier in our earlier experiments. We also showed large excess heat for those. This electrode we previously showed excess heat with, but we didn't seem to do something in a negative direction. So we're no closer on that annealing point as we were. We have, I should point out that we're now using very, very high purity D2O. We're using very high purity solvent, electrolytes, and we're using quartz instead of silicate. You can see that after 160 days of electrolysis, there's no heavy black deposits of materials that have been leached out of the silicon present on these electrodes. Previously, these electrodes were laden with very large amounts of black deposit, as we all know. When the thing boils dry, you have violent boiling, and you cannot control the cell. You can see some of the white deposit of the electrolyte left, and that's all.
Sorry, we are running out of time, so still one question on someone. Okay. The last one is from us after we get to stop.
And what's the maximum total megajoules of excess power or energy you have generated on a given cathode?
That excursion, it was listed on that slide, I think it was 294.
294 megajoules?
Yeah. Now, you can easily imagine 1 megajoule of error in any of those experiments. It takes, for instance, over the entire duration of the experiment, you add about 1 liter of solvent to replace what you lost in 100 days. And that requires to heat it up 25 degrees room temperature to cell temperature. That requires about 100 kilojoules just to heat this, just the additions. So there's always an error. So you can imagine changes in the atmospheric pressure, changes in the bath temperature, or any other ambient giving rise to similar errors. So the total accuracy, total precision is only about 5%.
And the total mass of the cathode?
Sorry, perhaps we are quite rounding out.
Sorry?
Okay. The mass of the cathode that produced 295 megajoules?
Was 1.2 cubic centimeters.
Thank you.
Okay, so thank you again. Mr. Thompson, now we are going to the next speaker, which is Dr. Celani from Frascati. He will speak about high power microsecond pulse electrolytics using long and thin line wire diluted LAOT DUO solution. Observation of analysis is key.
Okay, because we have done this time. Okay, because we have done some new experiment, we changed a little bit the title, and we speak about over past electrolysis, the new geometry effect and the new compounds, because it seems more useful for understanding what is going on. This experiment is done with the collaboration of several industries and NATO, and moreover, the plate the wire is from oil company and from Tanaka to NATO. Just a water advantage time this afternoon, some detection of new elements by same our old experiment, in our technical quality. The motivation is the following. We want to understand the origin of anomaly sheet and nuclear and moreover, we use as control parameters the resistance ratio and the sheet by its voltage flow calorimetry, and sometimes analysis of some new elements. Moreover, make a big effort in order to increase the detectability of these effects. It's well known about resistance ratio, today of nitrogen, palladium, poor palladium. experiment setup is very new, suspending some words. We used wires, twisted pair, very long, about 2 meters, and quite thin, only 1 micron. Distance is about 1 centimeter. Just to have an idea, the total resistance is 20 ohm, the wire, the weight of 160 milligram. The drawback of this configuration that the electrolyte is make a big parallel effect, so it's very difficult to measure the resistance, but we overcome this problem. One is reducing the electrolyte concentration. The second one, we develop a completely new circuitry in order to eliminate etching effect of electrolyte. Setup is like that, 2 wires, rounded, Teflon support, and glass, chemical glass. We can sketch the wire as a long resistance, the red one, and the main effort, the main view is the palladium is not connected to ground, but is floating from the point of view of the ground return. We use RC current for reference measurement. We use voltage as SI 300 volts and current up to 100. Moreover, we make a future study in order to understand the electrification effect from different point of view, and mainly about dynamic storage of the deuterium, loading and dynamic storage, and moreover we make a new geometry that we call collider in order to improve both deuterium loading and dynamic storage. In respect to the usual one using unidirectional electrification. She was the electromigration effect, was studied from Corn in 1929, that we increase concentration in proton conductors. The basic formula of electromigration is related to the voltage along the wire. So use long and thin wire with this voltage. Obviously, to increase this voltage and minimize the power of this dissipation, is necessary to use very, very long, very, very thin wire, or use material high resistivity. So suggested from the development before. The electromigration is a very powerful tool, but one very big drawback. You increase the concentration to one side, but after you have escape of the deuterium to the bottom of the wire. So it's necessary to make some physical barrier to avoid the loading. Usually people use gold, we use the copper or nickel, because the copper nickel has the advantage of reduce the lattice parameter of palladium. To speak about dynamic effects, because we have found from since long time that only the deuterium loading ratio is not important to get a chest heat. But it's important to have a moving of the deuterium inside palladium as fast as possible. Obviously, the pulse condition increases the moving because of very big power pulse. So the dynamic condition is equivalent to high speed of variation of concentration inside palladium. Is the approach of a new geometry of this experiment. Usually the people, when use electromigration, as the beginning of this point, but here can be leakage. So our idea is to put the bigger voltage at the center of the wire, so the deuterium can flow from this direction and this direction together. Is the maximum of concentration. And this geometry looks very effective to have large loading even in material like Mallove alloy that is enlarged, so easy to lose the deuterium. The other experiment used Mallove about 4% weight, and we studied about the sloping effect, hydrogen, and the deuterium, and we studied both geometry, normal wire geometry and general wire geometry. Used the yttrium because this material absorbs a very large amount of deuterium, up to 2.8 to 1, even at very high temperature. And moreover, has very large concentration compared to palladium, 2.5 times larger. So we can increase voltage drop along the wire. Bro, it is true, we can check if the theory is provided about electrical confinement of hydrogen due to large voltage drop along the wire. It's a test of some theory. So Okamoto, the center is palladium lattice. This element in the region is able to contract lattice. Most of the elements enlarge the lattice and are exothermic. The only exceptional point is lithium, is exothermic and reduces lattice parameters. Moreover, we want to understand why the pulse condition is very effective to increase loading and moreover HHS heat, and the limiting parameters and why the rest time is so important for this value. Typically, using pulse condition, we get a HHS heat is roughly twice that we can get in the best condition using this electrolysis. The drawback of pulse condition is impossible, almost impossible to have high accuracy resistance in measurement because noise induces from the pulse. This is one of the best results we get using pure palladium wire, quite large purity, after long operating condition of 4 months. The input power was about 50 watt. The gain in this condition was very large, up to factor middle energy gain, a factor of 2. This parameter we have introduced, blue line, give an indication of how much is strong the moving of the deuterium inside the palladium from the two sides of the wire, using the general wire geometry. This time we stop for a few minutes the electrolysis to check that it's all going well, and after we start again. And this is the resistance ratio. What happened? We have very large, very fast loading, and the fast loading means far large amount of HHS heat. Here the loading decreases, the speed decreases, and slowly the HHS heat decreases. So we stop again and try to get good condition. Just want to say at this point, the HHS heat drops almost to 0. In static condition, even the loading is very large. So just loading means nothing. It's necessary to move the deuterium. To stress this point, if possible. And start an experiment with palladium yttrium alloy is data from Sakamoto about loading and pressure dependence. And again, about the sense ratio, use of parameter, and loading ratio. There is a very strange anomaly for loading larger than 0.5, and moreover, there is a change, another anomaly between 25 and 50 Celsius. This is the results using the normal wire geometry in the electromigration. Current 250 milliampere total current, means 50 amperes per square centimeter. This is the value and the hydrogen. We have the time is a logarithm time of the point. The loading is extremely fast in comparison with pure palladium. Extremely fast. We never saw so fast loading this material, and after slow increasing. This is a similar results, but using center wire geometry. So this is the center, two center of the wire, and the end. So at the center, the loading is the material larger than at the end of the wires. So this proves that the center wire geometry and the electromigration is very effective to get large loading, always in logarithm state. This is the data. So this material in principle is not good to get chest heat because large lattice, but we get some loading, some chest heat. It's normal wire geometry because fast moving of the deuterium. This is the deuterium experiment. So after we take off heavy water and we put light water, the first experiment, the loading was about 8%. After about 10 cycles, dropped to about 3%. So the accuracy of our powder is about 1%. So it means, for some strange reason, with this material, even with light water, there is about 3% of the chest heat. Therefore, give overview of the experiment with palladium Mallove. So the best results we get in gender wide geometry went 22%. And they want to remark again with after several loading the light water, normal wide geometry give about 3% and the gender wide geometry about 5%. So if there is no error in our calorimetry, means the chest heat ratio between light water and heavy water is about 1 to 5. The main results are the following. We observe that the resistance ratio with the deuterium is larger than hydrogen, the material. The loading of geometry is larger than normal wire geometry. Chest heat of the water is larger than light water. And the chest heat of heavy water, gender wire geometry, larger than normal wire geometry. So these are correlated. And about the value of loading of this new alloy, since there are two components, one related to palladium itself, and other to the yttrium. Palladium is the maximum after the increase. Yttrium is slow increasing over time. To stress this point, the detection of chest heat with this lattice expanded material, the normal geometry, can support the idea that a large cathode voltage, because large resistivity of this alloy, is effective to confine in some way the deuterium inside the lattice as suggested from the data. Conclusion, or maybe just starting point for future developing. The paradigm Mallove is the peculiarity of a very large resistivity and good mechanical properties. It's not brittle and stable even after 20 cycles of loading and deloading. In proper winter condition, these materials always give a chest heat, always, even at a low value of 15-25% in comparison with the poor palladium. The advantage is don't need special pre-treatment. We use it as a received from Tanaka just into with solvents, and without conditioning by proper current steps. The beneficial effect of gender-wide geometry, said about 1 year and a half, seems in this kind of material very, very strong, and confirm what we have found with the poor palladium. So we are strongly thinking that the origin of a chest heat is the movement of the deuterium inside palladium when some large loading is reached. So together, large loading and moving. Obviously, the pulse condition is very effective to have strong moving because very large current density in a very short time. Thank you.
Now, before going to discussion, I have to make a short announcement by relevant to the last talk. Professor Pons wishes to dedicate his talk to Mr. Napa on the occasion of his birthday, which is today. So now the discussion is open on this paper of ceramic.
Could you show the current waveform in source and load and endpoint?
Sorry, can you?
Could you please show the current waveform?
Current?
Waveform.
No, we use, okay. This experiment, we use a DC current, just DC current. So what I showed before was the resistance changing over time of this element. So not just DC current. We study from 1 milliampere to 1 ampere, but no special wave. With pulse condition, we have a pulse with rest time of the order 1 nanosecond to the time 500 nanoseconds. But now I didn't show. So maybe some.
So you are not pulsing?
No, okay. In this, what I have shown now are the results with palladium and palladium 1. For palladium, to get large heat is necessary to have some preconditioning of the wire. Moreover, when we apply the pulse, the chest heat increases roughly factor of 2. So, but we don't understand why the pulse condition is so effective. In order to clarify this point, we used a new material that has some value that can enhance some parameters of poor palladium under pulse condition. So it's a side study in order to understand why the pulse is working.
Okay, so that's Makoeto.
I'm confused, usually confused, but I'm especially confused about your light water experiments and the light water results.
Me too.
Did you start your experiments with heavy water and add light water to them?
So I started experiment with heavy water and worked about 2 weeks. After take off of the heavy water, and they make a flow with light water once in order to clean the vein inside the palladium with anodic. And I suppose this was enough to clean completely the wire of residual deuterium. At the first experiment, the chest heat was quite large, less than in water, but quite large. So it was me for a big surprise. Later, I washed for about 10 times loading at equilibrium, since with the light water, the chest heat is 3%, normalized and about 5% in the one charge. It's about 1/5 instead of every water condition.
How long did you wait after you added the light water in form calorimetry? How many hours went by?
For a equilibrium time,
How many hours did you continue to perform calorimetry after the proton exchange for deuterons?
okay, the first experiment runs about 2 weeks.
Afterwards?
For the heavy water. After I wash, about 1 day washing, and after each day I move 1 or 2 days in order to clean residual deuterium inside the palladium. But even after 10 seedling, some residual chest heat. So explanation one, just some calibration error or 2 effects.
Okay, one question still.
How long does a palladium electrode last? How many hours?
Sorry, how long?
Yeah.
How long the palladium?
How long can you use it in an experiment? 1,000 hours, 100 hours?
Okay. For the palladium experiment that I showed you before, experiment works for more than 4 months. And give a lot of strange value, like resistance very close to 0. So it's very long previous story that makes this kind of wire easy to give loading. We have a clear chest heat. We have found one point. When the material give for the first time a chest heat, after give always, even if you deload. But until you don't get the chest heat, the first large loading, nothing happens. So the chest is like a beginner of something strange to give chest heat. Once, always one.
Okay, thank you very much again. Sorry, but we have no time for other questions.
Next paper is titled Some Thoughts on the Nature of Nuclear Active Regions in Palladium, presented by Dr. Storms.
I don't need to remind any of you of the difficulty and frustration in trying to find palladium that works. That's one of those more serious problems that exist in the field right now, although it's not very glamorous. Several years ago, it occurred to me that it may be possible to apply a pretest of palladium such that you could sort a batch of palladium into 2 piles. The one pile would have a very good chance of producing excess energy, while the other pile could be shipped back to the manufacturer for remelting without having to invest any more additional time. To implement this idea, Inner Materials very generously supplied to me 90 pieces of palladium that were treated in such a way as to produce 8 different sets. And I'd like to thank Dr. Ikegama and Dr. Kunimatsu for helping get this material. Also, Fred Yeager of Eneco provided some support for helping to defray some expenses, as well as did Dave Nago of NRL. I'd also like to thank my wife for allowing me to buy some constant temperature baths instead of some furniture that she wanted. It is still possible in this field to do reasonable work, make a contribution with very limited tools that are available to most any household. And I've tried to do that. The purpose of the study is to identify properties of palladium that are relevant to the production of excess power. And I will show you some of the properties that were studied. And to formulate a pretest procedure, which has been done. And then to find ways to treat palladium so as to produce additional active sites to make it active, even though it may not be initially. Tentative efforts have been made to explore that, but I won't get into that part of it. I have just a few thoughts that I would like you to go away with, I'd like you to remember. I won't have time to justify all of them to you, but a lot of the information has been published in Infinite Energy, and future work from this study will be published there as well. But let's look at the important points. Palladium is very non-uniform. In the world of palladium chemistry, that's like saying the morning will come after the sun comes up. It is, a motherhood statement is absolutely taken for granted that palladium is non-uniform and irreproducible. And that's outside of the cold fusion field. That reality has been difficult to accept by people in the field, but it's particularly difficult to accept by skeptics who beat on us because of the lack of reproducibility. It is the nature of palladium, not the nature of cold fusion that's at fault. Therefore, the material studies need to be made, and they need to be made in a number of samples. If you take one sample and compare it to another sample, this non-uniformity is such that it makes no sense. You have to do a statistical analysis. Average or bulk compositions do not represent the properties of the nuclear active regions. There's good reason to believe that palladium deuteride, beta palladium deuteride, is not the active material. It is something else. And theoreticians need to take that into account. It does no good to build a theory around a material that is not the material that's actually active. A pretest for the active material is possible. It is possible to separate palladium into these two categories. You don't necessarily get 100% reproducibility in the good batch, but it increases your chance enormously. An active material is very robust. That is, once you find material that is capable of making excess energy, it's pretty hard to cause it to quit. I mean, it's really quite robust, and I'll show you, if I have time, some evidence of that. You can do most anything to it. That means, and that's very important, because that means that if you identify palladium that works, and you have it, you can give it to somebody else or put it into another experiment and know that it will be totally reproducible. It will always work once it's worked the first time. Well, the properties that we're studying and that have relevance to the cold fusion phenomenon are listed. This is not a complete list of all of the variables that are important, but these are the ones that I have access to, and they do have a bearing. The limiting composition, and I know I might mention that all of these have been known for years. This is the first effort that I know of that has made a systematic study of relating them all together simultaneously. The limiting composition is obviously a very important parameter that's been demonstrated over and over again. It's the basis for a lot of the work that was described this morning. But it's the average bulk composition. If that bulk composition does not get above a critical value, you don't get any excess energy. Another one that has not been looked at to any great degree, that Carol, my wife, and I explored Los Alamos some years ago and has been known for almost 60 years, is the excess volume, and that is related to the crack concentration. Palladium, when it loads with hydrogen or deuterium, forms cracks. These cracks are microscopic, they're invisible under a microscope even, but they do produce a volume expansion of the piece that is over and above what you'd expect on the basis of its loading. And normal palladium has an excess volume between 5 and 6%. At that level of crack concentration, you do not get excess energy. If you, every once in a while, you'll find a piece of palladium that has either between 0 and 2% excess volume. That palladium has a very high probability of producing excess energy. The open circuit voltage is a way of measuring the chemical activity of hydrogen in the surface. And if I have time, I'll show you evidence that indicates that the production of excess energy is preceded by the formation of a phase on the surface, which is quite different than normal palladium deuteride. And the excess energy forms only if that phase forms. The bubble pattern during deloading was looked at. This allows one to see the inhomogeneity. If you take a piece of palladium and put it under acetone and look at it with a microscope, you can see the bubbles come off. And they come off, you can see the cracks, the lines of bubbles. You won't be able to necessarily see anything there from which they're coming, but they're nevertheless coming out. And there's a variety of structures that exist that from which the bubbles come. But frequently there are regions on the piece from which there are no bubbles. And I believe that that's the region where most of the activity, the nuclear activity is taking place, hopefully. The deloading rate is determined by taking the sample out of the cell, turning off the current, starting a clock, and measuring the composition as a function of time. If you plot V over PD ratio as a function of the square root of time, most of the time you get a straight line. And in palladium you have to say most of the time because there's always an exception. But you get a straight line, and the slope of that line gives you a measure of how effectively the hydrogen is leaving the sample. Now, the loading, I have adopted a standardized loading technique, fixed current, fixed time, fixed temperature, so as to be able to compare the behavior of these samples without the other variables. I've explored the effective temperature, the effective time, the effective current, but I've just chosen an arbitrary one. And the loading goes up like this, and then reaches a constant value after some period of time. And I do this for 24 hours. And the open circuit voltage also rises, and if it's going to make excess energy, this will have to continue to rise. One would expect no excess energy at this low value. We'll get into a little bit of that later. If you compare the loading behavior in terms of a histogram, you get a characteristic behavior that is applicable to almost any property. There'll be a range of values. This is pure palladium, and you can see that for no apparent reason, the loading went from 0.76 up to about 0.85. I was able to use this material to compare the effect of apharesia. These samples that are not colored were not treated with apharesia. The apharesia treatment tends to make the loading more predictable. That is, it brings it into a narrower range. And so it's beneficial in that sense. However, it clearly brought it down from what's available in the absence of apharesia, but it brought it up also. So it works both ways. The effective boron was explored, I had enough samples to make it look, have a reasonable statistics. Boron has a wider range of stoichiometries available to it during loading. And the Makoeto does the same thing. It tends to focus the composition at one particular value. But I might point out that as a criterion for eventual heat production, if the sample has a composition below about here, down in this region, it's not going to make excess energy. It's only these samples here that we'll keep and put into a pile for eventual study of excess energy. The same can be said of the excess volume. The excess volume also has a range of values. This is pure palladium, and you see it goes from 1.5% up to 10%. For no apparent reason. I mean, many of these samples were from the same piece, adjacent to one another on the strip of palladium that was being made. So there's no reason why we would expect it to be different, but it is. Okay, thank you. If, on the other hand, you look at the boron shifts it up and makes a lot of material that has a very high excess volume. In other words, boron is undesirable from that point of view. So let's look at the open circuit voltage. That's one of the very interesting measurements in what we can make. It's determined by measuring the voltage between a platinum reference electrode and the cathode during a time when there's no current flowing between the anode and cathode in the cell. This tube is filled with electrolyte and that provides the conductive bridge. The platinum reference to pure palladium has essentially maybe 20 millivolts difference. But when it's loaded, when the palladium is loaded with deuterium, the voltage goes up to quite reasonably high values. This is an example of a piece of palladium that produced no excess energy. It was loaded, it went an open circuit voltage of about 0.75. This was allowed to deload while the open circuit voltage was measured to show how it changed as the composition changed. And you can see it drop down to the alpha phase, and if it had gone long enough, it would have gone back down to zero. That's an example of a dead sample. A material that has made excess energy, or was in fact making excess energy when the sample was turned off, 4.5 watts, shows a different effect. Here we have an open circuit voltage which is very large, 1.25 volts. I've seen values somewhat higher than that, but that's up in the high range. If that loading is turned off, so it's allowed to deload, you see it come down, but then there's a little rest here and it goes down again. If this current is followed, if this curve is followed on down, it behaves the same manner as the one I showed previously. That is, it follows on down and then drops down to zero. In other words, this is characteristic of the beta phase, but then there's something else on the surface which was not present in samples that did not make excess energy. And I believe this is the nuclear active phase that is required to be made, and it has a much higher composition, or at least a higher chemical activity than does beta palladium 0. Now, I won't have time to show you the calorimetry and the heat measurements. Please be assured that I have gone to some trouble to do accurate calorimetry. I have samples that have made excess energy. Here's a list of the various ones showing how the excess energy relates to these various parameters that I was measuring. And just as a general trend, you can see that those that have a very low excess volume are the ones that are making excess energy. Those that have a high excess volume are not. There's a few exceptions in there for various reasons. I mean, one of the characteristics of the flame is if you have too much reproducibility, I worry. That shouldn't happen. I'd like to show you a representation of what I think the surface of a piece of palladium looks like. These blue regions are